So hello friends, today I am going to show you how you can easily create the simple spring mass damper system into CREO 2.0. So it's very easy to understand this kind of the simple vibrating system into the designing software, and you have a good visualization for that thing. So first of all we make the mass, then we will make the first fixed support for that, then apply the spring damper, and then we analyze the system. Okay, first of all we make the mass, so take it name as mass 1. Okay, then choose your units that you want to design create your part. So I am taking right now mm's. For simplicity purpose we take only a extrude command and make the part as a rectangular only, and make a habit to draw a center line first of all, so you can easily identify where is your coordinate point is. So first of all we make 100 mm by 100 mm square. Okay, then symmetric this object about this xy plane and take the dimension, it's 100. So we have the cube of 100 mm by 100 mm by 100 mm. Then select this point command and create a point which is the intersection of this plane, front plane, and this right plane and this top plane. Okay, so we have the point 0. Then make an axis which is passes through this point and perpendicular to this plane. Okay, so we have this point and the axis for this mass. Then save this assembly as per your required directory, so you can recall. Okay, save it, then create a fixed support for this mass oscillator. So for that make a support, name is at support 1. Okay, select units. For simplicity purpose I am only make one rectangular for the support. So define this plane, let's say top plane. Okay, so make only a simple rectangular for that, let's say 200 mm by 200 mm. Okay, and take the thickness that you want. It doesn't matter, it will not going to be any kind of effect on our analysis, but for our simplicity purpose we take this 30 mm. Okay, then similarly here take the one point which passes through this plane. So we have this point 0 for this fixed support. Then make an axis which passes from this point and perpendicular to this plane. Okay, then save this support part, then make an assembly of this two part and select this assembly menu and name it as simple spring mass damper system, simple spring mass assembly. Okay, choose your units, let's mm. Then first of all make choose your component that you earlier created, support 1. Okay, then by this menu, default menu, you can directly coincide your geometry's 3 planes to this assembly plane, so no need to manually go and select and coincide each and every planes. So it's very easy command for that. Okay, then select mass 1, and then we want to make a slider mechanism, that means this mass is oscillate about some fixed support. So from that we select the slider constraint. So here the software is asked about this axis. So we select two axes. Let's say first axis is this mass axis, and the second axis is this fixed support axis. So from that we say that we configure this axis. This mass is aligned with this axis of this assembly axis. Then we have to apply the rotational constraint. So we have to select two planes which is parallel to one each at this mass and another is at this fixed support. Then give the translation axis. So select this plane and select this plane. So software is automatically inbuilt. It has value around -239, but let's say it's -500. So this plane and this plane has a distance right now is -500. Then mark it at set 0 point. So always software takes this distance as 0 and select this enable regenerate value. So whenever we are doing the analysis and after analysis my mass is not here this at initial condition. To keep it at initial condition we have to regenerate this assembly. So we directly come this configuration, then select OK. Now go to the application part and mechanism and select this spring menu. So here we want to create spring from this fixed support and to this mass. So you have to choose 2 points. First point from this fixed support and another is from this mass. So automatically software is directly generated the spring like as now here we have to select what is the spring constant of this. So let's correct this unit of it. Let's say it is Newton per meter, sorry. So then apply the spring constant. Let's say it's 1000 Newton meter, then OK. So automatically we have this spring inbuilt, and this by drag components we create this assembly like this. So we have the animation, we have the visualization for that. It's spring is behave like a virtual spring, then OK. So from by this simple spring mass system assembly, it is the name of this assembly. Then right click here and regenerate. So our assembly will be converted into directly in our initial position. So now here this is mass property. So here we can directly assign the mass of these objects. So click these objects, then select this mass property. Here right now the unit of mass is in terms of tons, but we convert into kg. So let's say the mass of this object is 5 kg. So we have to divide it by thousands. OK. Then apply and OK. So we have the mass of this 5 kg and the spring constant is 1000 Newton meter. So first we analyze static analysis. We will take a static analysis for that. So here this is a static analysis. Then enable this gravity. So due to the gravity it has weight, and due to that weight our spring going to be deflect. So run this analysis. So around some static deflection is occur over there. OK. Now how much will be the static deflection? We will see by our numerical methods, analytical methods. So I am using the PTC method for that. Here our mass is around 5 kg. Then stiffness of the spring is 1000. So the natural frequency of this system will be omega n will be √k by m. So the natural frequency right now the software is showing 14.142 radian per second. Now we convert into the time period. So t time period t will be is equal to 2 into pi. For pi I am directly write 3.14 divided by omega n. So from there time period will be 0.44 seconds. Now we'll see this is time period, and now what should be the static deflection. Then so for static deflection we have to use the static deflection equation. For that deflection, let's say d is equal to weight will be is equal to mass into 9.81, so it will be the weight of this mass divided by spring constant k. So the static deflection in terms of meter will be the 0.049. now to convert it into mm we multiply by 1000, so the static deflection is 49.05 mm as per our analytical method. Now we say how much is the software is showing static deflection. For that we go to this measure tool and select this analysis definition 1, and here take a new measures. Here we want to show we want to measure the static deflection of it. So here mark this is the what kind of the analysis that you want. So first of all we select the position, then select the point. I am selecting this point, then then select the coordinate system that you want to measure this point. So select this assembly coordinate system, then magnitude, let's say its magnitude is y-axis because y-axis in this downward direction. So here this arrow will be indicate your chosen component, so apply. Okay, so then from this point we will say that what should be the deflection of this spring. So from that this point, as you select this point, so it will be indicate this 49.033 mm around, but because initially it has a deflection of because it has initial distance is 500, but the more distance it is minus 549.033 mm. Now we will take dynamic analysis of this system. For that again we have to go in mechanism analysis, then make it dynamic analysis, then enable gravity. Okay, for that first of all we have to regenerate our system, because it is not in our because this system right now is in equilibrium condition, so where there is no any kind of vibration will occur. So for that we select this and regenerate our assembly, so our initial condition can be directly achieved. So go to this mechanism analysis, then select this dynamic analysis, then enable this gravity. Okay, then run the analysis. So as we see this system is going to behave like a vibrating system. Right now we are doing the analysis about 10 seconds for only 10 seconds. Okay, now see how the behavior of this system is. For this select this measure, select this analysis definition 2, and select this measure and plot the graph. So here it's look like a dynamic system of like this. Here format data and select this none, so this kind of the circles will disappear for our good visualize purpose. So apply. Okay, so from these are the waveforms of our system. So to complete one cycle, here it will complete one cycle, and as you click this point, so here this is time period will be shown here, because here to here there is one cycle is completed. For that the time period is showing by analysis is something like 0.44.669 seconds, and as we have the result, analytical result for this system is around time period is 444. So it seems like good. So it seems like good. Our analytical and this analysis are both are same. So now the third thing, we are applying the damper to our system. So it's very similar, it's also very simple to apply the damper for this system as we have done in the spring. So here in the below of the spring we have this damper option. Select this damper option and this apply the damper between to that point. Okay, so directly we apply this damper over here. Then select the units of damper. Right now I am using the Newton second per meter for the unit of our damper, and software has the viscous damper right now. Then let's say damper value is 1 Newton second per meter. Enter. Okay, so as we have introduced our damper, so my amplitude will be gonna be decrease consequently due to this damping present in the system. So regenerate the system, then again make a dynamic analysis, enable gravity, and then run the analysis. Okay, it will take some time to doing this analysis because we have introduced our new damper into system. Okay, now we measure the how my waveform are. So as we introduce the damper into our system, my waveform, my amplitude of the system is consequently decreases. So likewise I can say that it's a underdamped system. Now we will see the what should be the criteria for a system to be behave in the critical system, then overdamped system and underdamped system. So as we have the mathematical formula for the critical damping system, so for critical damp system, my damping value, that means critical damping value is around 2 into under root k into m. So k into m. Okay, so my value of critical damping coefficient will be 141.42. As I have the value of critical damping as 141.42, so my system behaves like a critical damping. That means critical damping is that situation at which my system has no vibration. So I am copying this value and put it into the my damper. Paste this value and then okay. Now I regenerate my system. Then again I am going to analyze my system. External enable gravity. Run the system. Okay. Now we will see how is my waveform. So as you see that there is no any kind of the vibration is occur on the system because we have the damping value which is a critical. So there is no any kind of the vibrating phenomena will be in my system. Now as we now we will compare this all three phenomena. Okay, so press the control and select these three analysis definitions, and here select this also measure and plot the graph. So we will have the three comparison over there. Here for good visualization purpose, select format and data, and here this is the point display and select the none. So here we have the good visualization for this and apply and okay. So first of all sorry, I convert this color for that. Let's say its color will be something like this. Okay, so we have good visualization for that. Apply okay. So as we see in our first graph, this graph, as there is no damper and there is no damping and there is no decay of my amplitude, but as I am introduce damping, but which is under damped value, so my system is in the under damped condition and my amplitude is going to be decrease exponentially. But as my value of damping is almost a critical value, then my amplitude is drastically decreased to 0. Now we will apply the damping value which is above my critical value. So let's say applying the value of this coefficient around 200 and then run analysis my system. Select this dynamic analysis, enable the gravity, then run the system. Okay, measures, select this our measure one. So as you see, the my amplitude is gonna be, there is no any kind of the vibration occur because my system is in over damped conditions. Now we compare all these for our analysis. Okay, so as we have the all the 4 result we have here, remove the circle from this graph so we have the good visualization for that, and change the color of this. Okay, so as we have the 4 graphs, first of all we have graph about there is no any kind of damper. In second one, our system is behaves like the damped system, because also it has the vibration. But as we have this graph, it is about critical system, and this system is more decayed its amplitude as compared to our over damped system. So this is all about our 3 vibrating system. So likewise we have this is CREO parametric has a good tool to understand this kind of systems, as well as more complicated system that can be also understand and design into this kind of software. Thanks for watching this video.